Today topic is about laser Doppler anemometry. The laser Doppler anemometry is otherwise known as LDA, where this laser Doppler anemometry is used. If you want to measure the velocity of the flow of liquid, then we can go for LDA method. What are the advantages for this LDA? LDA is generally it is a measurement of fluid velocity by detecting frequency shift of laser light that has been scattered by small particles moving with the fluid, and this is the method non-destructive. Not only that, this is also called non-invasive velocity measurement technique. So why it is a non-invasive velocity measurement and why we have to go? Because for the normal method, suppose like if the people are using with high temperature fluid or high pressure fluid, and if it is corrosive and if it is chemical, then direct measurement we can't able to go. That is the reason the people used to go for non-destructive method as well as non-invasive method. That are the major advantages when you are going for this LDA method. So laser Doppler anemometry. So the principle inside LDA is Doppler shift. What is Doppler shift? How we are determining the velocity using this LDA meter. So in LDA meter, the velocity is measured through observing the frequency shift or scattered light. It is a measurement technique. It is used to measure the fluid velocity by detecting frequency shift of laser light that has been scattered by a small particle moving with the fluid. That was the principle. In laser Doppler anemometry, it is a technique used for measuring velocity. They are calculating the frequency shift of the laser light by a scatter from the particle moving with the fluid. That was the principle inside LDA concept. Now you just look at the diagram here. This is what called laser light source. So you all know laser light is in monochromatic nature, and it is a directional signal. Then the signal to noise ratio is also very low. That is the reason we are going laser light source. So from the light source from the laser, which will be captured through a lens, then that will be passing through the fluid. So in the fluid particle, the rays are getting, it is beam splitter, then you have a rays, but all the things together, it is coming into interest. This is the path of the fluid. Here only we are going to measure the velocity of the fluid. So after that, whatever the rays coming out from the fluid is captured via the lens. Then finally this will be received through the detector or receiver. So here you will have two signals, that is F plus Fs. So Fs, which is nothing but after shifting whatever the scattering light we are having, so this Fs is an additional shift of the signal, and F, which is nothing but the incident signal, that was the input. So now you just look at here the intensity of the light, which depends upon the medium and the light source. So whatever the signal intensity, which was calculated by what medium we are going to use, as well as what type of light source we are going to use. From those two components, the intensity variation will be there. You can just look at here the incidental signal. That is the reason why there is a suffix I. So Fi is an incident frequency, wavelength frequency, incident on the point, and here this is the particle. The particle is getting scattered in all the direction, and one of the signal which was received through the receiver point. So the scattered light with a velocity, it is moving on the way to the medium. So you all know how there is a relation f lambda which is equal to c. So through which we can calculate the frequency, that is c by lambda. C is speed of light, that is 3 into 10 power 8 meter per second. F is in frequency and lambda is in wavelength. So using of this particular formula, we can able to calculate the value of f. So we are concentrating here the incident light. So we are just writing Fi, which is equal to C divided by lambda I. So in presence of a particle, what will be the frequency? In the before thing, you can just look at, I am just going to have two direction. One is another I, the another direction is J. So if it moves on the medium, what will happen? There will be a shift. So that shift will be indicated through incident on the light for the velocity of a particular medium. So whatever the signal I am getting, that will be subtracted from the speed of light. So the particle shift, that is frequency, in presence of particle, the frequency shift is C minus unit vector of I unit vector divided by lambda. If the same one, if you are calculating in opposite direction, then that will be, we are taking into negative. So you will have C plus V into I. So in either it is in upward direction or it is in downward direction. Just I would like to explain with an example. Suppose if there is a blowing of a horn, what will happen? If this is in source, this is the blowing of a horn. If the person is standing this side, if the person is closer to the source, what will happen? He can able to receive the signal with high intensity, that means high velocity. If the person is moving away from the source, what will happen? The intensity variation will be there. Accordingly, there will be a velocity variation is also there. So there will be a frequency shift. So that is what actually happened, this particular expression. So if there is an opposite move, then it will be in positive shift, that is I will be in negative. So F suffix I, which is nothing but frequency of incident light. So in another direction, if you are concentrating, then according to this lambda P, which is, this is nothing but the wavelength of the particle. So wavelength of the particle is C by Fp. Already we have derived the expression Fp. So when you are substituting, you will have C into lambda I divided by C minus V into unit vector I. So the same thing, if the same wavelength, I am just going to calculate it with respect to the medium from the source. That means if the medium is getting moved, then the C will be replaced through the another direction, that is C minus V into J unit vector divided by Fp. So here only thing is C is replaced with C minus Vj. So this will be indicating the opposite direction. So the source is also getting moving, so lambda S. If it is in opposite direction, so here this lambda S, which is equal to lambda I into C minus Vj caps. That means whatever the value I got through this particular expression, that was substituted over here in the general formula, that is C by Fp. So instead of this C, I am just substituting C minus Vj unit vector. So here also you will have the same thing. So here this I and J are the unit vector. So if the scattered light is moving towards the receiver, you will have Fs, which is equal to C divided by lambda S. So already you are calculating the value of your lambda S. So I am just going to substitute this lambda S value over here. So C of C minus Vj divided by lambda I of C minus Vj you will get. So whatever the signal on incident as well as the scattered one, that will give you the frequency shift. That is what Doppler effect talks about. So Fs already you have calculated, and Fi also you have already calculated. So if you are substituting the thing, you will have C by lambda I of C minus Vi by C minus Vj minus C by lambda I. So if you are multiplying the term, that C term will get cancelled. So finally we'll have C by lambda I of Vj unit vector minus Vi unit vector divided by C minus Vj unit vector. So this is how the frequency shift we can calculate it from the incident and the scattered one. So if the incident and the scattered one is known, then we can able to calculate the frequency shift across those two signals. And the velocity is always less than C. So that C minus Vj cap, that is unit vector, we are just going to substitute it with C because of a very small value. So your frequency shift is become Fd is equal to C by lambda I of V into J cap minus V into I cap. So if you are taking out that V, you will have J cap minus I cap. So the frequency shift has been calculated using this Doppler shift phenomena. C is velocity of, speed of light. This is wavelength, and velocity. J and I are the unit vector while it is going on the direction flow. So if you know these values, then we can able to calculate the frequency shift, either I vector or J vector. They are the scattered one, so through which we can able to calculate the velocity. So if you know the values of this speed of light as well as the wavelength of incident one and the unit vector, then directly we can find out the value of frequency shift using this expression. So this is how Doppler shift principle, which is working on LDA. Then another one is advantages. Advantages of this is non-intrusive method, and there is no calibration is required. Many components can be measured, and it has a spatial resolution, and it capable of tracking very high frequency fluctuation. Then what are the limitations when you are coming across this LDA module? Because of light scattered by a small particle, there will be a weak intensity and noisy signal. Random location of scattering particle in the fluid, it also creating a new problem of data analysis, and the data arrival which are randomly and infrequently. And moreover, the optical arrangement is sensitive to vibration because we don't know how it is going to arrange it in proper way. So there will be a problem of vibrations. So these are some of the limitations of your LDA. So this is what the basic concepts of LDA. We have two more methods of LDA also. One is single beam, the another one is double beam, and how it is working. These things we are going to see it in your next video. So I think you understand, right? Okay, thank you.